So there were some questions about this enumeration kind of business. So let me go over it one more time. And we'll use basically the same algorithm for high-dimensional expanders. So let me go over this. Before the break, we kind of said we can find this partition generated by the functions that we get in the regularity decomposition. And maybe one way of stating the claim is that if I have any two functions f and f prime, which have the same expectation on each piece of this partition. So they have the same fraction of ones and minus ones. They can be very different functions. They just have the same expectation, the same statistics on every piece. Then f and f prime have the same inner product with every function in this decomposition. And so they have the same inner product with h, whether I look at f tensor f or f prime tensor f prime, I get the same value. Right? And because this is very close to what I get here, both of them have the kind of very same correlation, like very similar correlation with G, up to this epsilon error. So I could output either of them, it doesn't matter. Okay, if f is a maximizer and if I output f prime, it's only going to be epsilon far. It's not going to be too bad. So out of functions which have the same inner expectation on every piece, I could output any one. You can think of this kind of being the same, having the same expectation as an equivalence relation, and I could output any member of each class, right? It doesn't matter. It has to be in the right equivalence class. And in fact, it's okay to even have approximately the same inner product. This is no longer an equivalence relation, but it's approximately the same inner product, like expectation. So now, yes, well, not the points, just the expectation. So let's see. So suppose I'm going to guess a number for each piece, which is some number here. Okay, so let's say I guessed a number which is 0.2. So there's only 1 point. Right. Good. So, so there are basically this whole space is of size n. Things which are very, very small, which are kind of smaller than gamma, I'm just going to give them 0. They're not going to contribute anything. I don't care about them. So let's assume each piece is reasonably large so that 0.2 makes sense. And that just means it's like 1 60% of the time, minus 1 40% of the time. I'm going to pick an arbitrary set of points which are like 60% of the space. Label this function 1 here and minus 1 here, arbitrarily or randomly, whatever you prefer. Okay, and that's going to be the function which realizes this guess on this piece. Okay, so for every guess, I'm just going to pick something which realizes that guess on that piece. This will give me a global function. It's just as good as any other function realizing the same guess. It has the same expectation. Yeah. So basically, slices which are small are kind of really small because this expectation is uniformly over n. Right? So if the slice is very small, it's just not going to contribute anything. I can just put 0. It won't matter. Okay. So is that more clear now, this part? Okay, good. Yeah. No, because I basically pit each piece with probability proportional to its weight. So gamma is a uniform error. It translates, like it doesn't need to be as small as 1 over the number of pieces. It just needs to be like epsilon square or something. It's because, I mean, if I pick this piece with probability 1/3, this with 1/2, this with 1/5, and so on, and I have gamma error in each of them, I still have gamma error in the global average. Yeah, so it doesn't need to be exponentially small. Okay, any other questions? All right, good. So now, let me go to high-dimensional expanders, or in fact, slightly more general objects, but let's draw them as complexes. So at the very beginning, we kind of phrased decoding this direct sum code as a function now defined on k, like k faces of some complex of with set size k and so on. Okay, and let's maybe draw that as a part-type complex again. Let's say I have k layers, okay, and I sort of have hyper edges of this form, which correspond to faces of the complex. Mm. Okay, so I'll call this kind of a complex splittable. I'll kind of define a property. So I'll call it, sorry, let me write here. Lambda splittable if for all L, which is, let's say, in one K minus 1, if I split this complex into the first L layers and the remaining K minus L layers, and what does it mean to split this complex into these two parts? It just means that I think of a graph where I will have one vertex for L tuples, which participate in some hyperedge, and I will have a vertex for K minus L tuples, which participate in some hyperedge. It's partite. So when I say K minus L, it always is the last K minus L. And when I say L, it's always the first L. So let's call them X1 to L by slight abuse of notation, and X L plus 1 to K. So for every hyperedge, I take its first L coordinates, make it one vertex, and take its last K minus L coordinates, make it a vertex. Okay, and then I draw an edge between them if they together can be combined to form hyperedge. So there might be many hyperedges which have the same first L coordinates. So this vertex might have some large degree, right? But constant, right? It's whatever is the degree of this hypergraph. If this complex is sparse, then so is this. Okay, and this is a bipartite graph. This is one side of vertices. This is another side of vertices. Okay. If this graph is a lambda expander. Okay. So what does it mean for a graph to be a lambda expander? Second eigenvalue of the normalized adjacency matrix and so on. I'm not sure this is going to be regular and so on, so we might have to do some funky weights in the matrix, but we'll talk about a very simple example where this is even regular and so on. Okay, so, but for all L. So there are K minus 1 graphs. I can construct this by looking at the first coordinate of every hyperedge and the last K minus 1, or the first 2 and the last K minus 2 and so on, the L graphs. All these L graphs are expanders. If I have this property, I'll call this complex splittable. Okay. Is this definition fine? Okay, very good. And sorry. So once I split it at L, it's a bipartite graph. One side of vertices are first L coordinates for each hyperedge. The other side is last K minus L coordinates for each hyperedge. Okay, and there is an edge if this pair together participate in the same hyperedge, right? So again, there might be many hyperedges which share the first L coordinate, so this can have large degree, large constant. Okay, good. Yeah. At most the number of hyperedges. I'm not drawing it. Yeah. So it's not n to the L. It's whatever is the number of hyperedges, at most that. Okay. So let's see a couple of examples. So I mean, it takes work, and it's a result of Dickstein and Dinur, and also independently we proved maybe a slightly weaker version of this. That if you have lambda local spectral expander, then it's of k dimensions, then it's order k square times lambda splittable. But that's a more, so I don't necessarily want to talk about that example. Let's talk about a simpler example. Let's talk about expander walks. So now it's a partite complex. I can think of ordered walks and so on. And let's talk about expander walks with 4 edges, or 4 vertices, 3 edges. Okay. So every time so I have some underlying graph on which I take walks of length 3. I see 4 vertices. Okay, I think of this as a hyper edge. So I put one copy of vertices, another copy of all the vertices, and so on, and I connect them if they are together in some walk, right? So this is I can think of this as a complex, expander walks complex. We talked about it, right? Okay, and I claim this is splittable. So I mean, the interesting split is when I kind of think of it as the first 2 coordinates of every walk and the last 2 coordinates of every walk. And I'm thinking of this as a bipartite graph. And if it's a bipartite graph, I'm talking about the singular value. It makes it a little easier, sort of in terms of expansion. Okay. So let's write down the adjacency matrix of this bipartite graph, which is a bipartite graph. Okay, first of all, what are the indices for rows and columns? So how many rows do I have? How many columns do I have? There are, let's say, walks in kind of deregular G on n vertices. Okay, so suppose I have a graph on that I take walks of length 3, okay, and I try to write down this bipartite graph corresponding to this splittable complex or whatever. How many edges, or how many rows do I have? Number of edges, because the first 2 tuple has to be some edge in the graph, right? Always. So maybe I'll move a little. So the rows and columns are actually indexed by edges. Okay, and let's think of I1 and I2, which is an edge. And let's think of I3 and I4, which is an edge. And okay, now when is there a 1 in this entry and when is there a 0? So if I have I1, I2 and I3, I4, when can they be combined to form a walk? Exactly. So it just says it's a 1 if I2, I3 is an edge. Okay. And now if you sort the rows of this by I2 and sort the columns of this by I3, we are calculating singular values. So we can apply arbitrary permutations to rows and columns. It doesn't change the singular values. Okay? These are just unitary transformations. So then this matrix is nothing but the adjacency matrix of the graph tensored with kind of the all ones matrix, d by d all ones matrix. Because for every I2, I3, there are d ways of extending it to I1, and there is d ways of extending it to I4, the I3 to I4. So then for every I2, I3, I will have one block here, which is a d by d block of ones corresponding to all the values for I1 and I4 I could have chosen. For every edge, there will be this d by d block. That's it. That's the whole matrix. And now if you take a tensor of 2 matrices, the eigenvalues are just product of eigenvalues. If you normalize correctly, the eigenvalues of this are 1, then whatever is lambda, 2, and so on. The eigenvalues of this after you normalize is just 1, and then all the other eigenvalues are 0. Okay? So the second eigenvalue or the second singular value is just the second singular value here times 1 here, which is lambda times 1. So it's just lambda splittable. Okay. So expander walks, and nothing special about this. I can draw this one, but you take a longer walk, the same argument applies. You just look at a longer d by d matrix, but it's still an all ones matrix. It's only one non-trivial eigenvalue and so on. Everything is the same. Okay? Right. So expander walks are splittable. Also, importantly, the kind of zigzag walks considered by Amnon in his paper are splittable. So this property at least is not vacuous. It actually holds for a lot of interesting complexes. And I'll claim that we can do the same reasoning for this. So I'll just kind of state something without necessarily proving it. But it's not too complicated. So, okay. Everyone on board with the definition of splittable complexes? Yeah. 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 Yes. Yes. We reduced it to solving a CSP on that HDX. CSPs on expanders. Right. Now I claim the same algorithm also solves CSPs on splittable complexes. So I'll mention the key part. Right. So now, I mean, again, if we look at the right-hand sides, we will have some X, and we will now, if you look at the sum of k things in this world, they will kind of correspond to functions. And what one can prove is a splittable regularity lemma, that for any G, there exists an H, which is now such that this H is a good approximation of G in the sense that for every f in this function class, G minus H f is small. Now you'll need a stronger condition on lambda versus epsilon, but I mean, it's like lambda is less than equal to, I don't know, epsilon cube, maybe times some function of k. But I don't remember the exact function, but it was still something which was polynomial in k, if I remember. So nothing too bad, okay? But yeah, maybe some constant. Okay, I don't remember this exactly, but the proof is not complicated. So yeah. No, I kind of cheated, right? Weak regularity, when I started applying it, I kind of had this inner product on edges, and I changed it to inner product of the two functions, right? Fi1 inner product f and Fi2 inner product f. That required expansion. There I used expander mixing lemma. Right, so you can build that into the definition of this. Just say that, so this is a version where regularity lemma is with respect to inner product on edges. You can directly state a version of the regularity lemma which is with respect to inner products on n tuples, independent, and build where you will need lambda. So so usually we just do that in the statement of the lemma, so it's easy to apply. Don't have to do that every time you apply the lemma. But yeah, it's completely isomorphic. You can do it either way. Oh, sorry. Oh, here, yeah. So there I need lambda. I mean, yeah. So now, yeah, it depends on what this inner product is. And I mean, I will have to also normalize this by, in the expander, if I want to do this, I should actually multiply this by d over n. And in there, I will have to apply by d over n to the k minus 1 or something. So I'll have to modify the statement, but it's morally the same statement. And the proof is also the same. It's, you kind of think of your complex, and you think of it as a bipartite graph between like the first layer and the last k minus 1 layers. Prove a weak regularity lemma. Okay, and now the last k minus, so now you have function which is some function of this and some function of the n minus k tuple, or like n minus 1 tuples. Okay, then you again split this function. Again apply another regularity lemma. Keep going. So it's just an induction. You have to be careful about in the induction to get the right parameters, otherwise they blow up. Takes a bit of work. And I mean, algorithmically proving it requires a paper, but it's the same statement. Once we have that same statement, you get exactly the same kind of guarantee, except now you have k functions for each term. And then solving the CSP is still exactly the same. I just need to look at the partition generated by all of them, and this time there will be k over epsilon square times some constant. I guess the densities in every piece. I realize it in an arbitrary way. and that gives me the same inner products, and by the approximation guarantee, the same value of the CSP. So it's exactly the same algorithms once you have this regularity decomposition. Proving this, I mean, conceptually, the proof is not complicated for existence. For algorithm, you need to work a bit, but I'm not going to go there. But actually, this algorithm can run in near linear time, randomized. So you can compute this decomposition in near linear time in the size of the complex. So it actually gives you a relatively fast algorithm for decoding. Yeah. Yeah, so you're saying I need to be able to split every subset. It actually, you can derive it from there by marginalizing. So because it's singular value, you can look at functions which are like constant on some part and only vary on the second coordinate or something. So this condition implies the one you are thinking of, maybe where you look at and split a subset of things. Actually, we wrote it first with that, then we realized we didn't need to. So, yeah. And just like Max was saying that you can think of all of this in terms of probability spaces, this condition actually also was studied independently as a way of higher order correlation of k-tuples of random variables. I think Elkhanan Mosel was one of the authors. Sorry, I don't remember all the authors. But yeah, so this condition comes up as also in the study of probability, the same splittability condition. You have the maximum correlation of any function, any pair of functions where one function only depends on the first L things and the second function only depends on the last. That's just singular value. Okay. Any questions? Yeah. No. Yeah. Yes. I mean, yeah, no, I don't know. It's a good question, but I don't know a good answer. It's no, so maybe you don't need splittable regularity. Maybe you get some other kind of approximation, which also follows because these sets also have nice overlap properties. We just gave up on all of that. I mean, for us, it was for decoding Amnon's code, it's useful to give up on all of that because if you just do it with an HDX, you don't get very good rate. And sort of the rate is the whole point in that code. So you have to work with some sparser complex. But yeah, it's a good question if you can get more using HDX. I don't yet know how to use it. So, okay. Other questions? Okay. So now I'm going to switch gears a little bit and talk about this other definition of CSPs on HDX. Okay, so we're back on HDX. And now I'll talk about how to prove things are hard, or sort of kind of talking about the other kind of CSP construction. Yeah, so if regularity is not your jam and so on, you can forget about all of it and we'll just start from scratch. Okay. Okay, so now we will talk about this other construction where we thought of variables being on the edges as listed. And now I will really think of three array CSPs. It will just make my life a little simpler. And okay, first of all, why should we bother about proving, again, studying CSPs on HDXs? So, okay, there it gave us some codes. What do we get now? We are proving it's hard. So it's like a lose-lose exercise. I consider a weird problem and prove that you can't solve it. But the point is, one thing we want to do with HDXs is use them to construct PCPs. And if you think about PCPs, it's just like a CSP on steroids, right? It's you start from a satisfiable SAT formula, you convert it into some PCP where the verifier checks some bits and so on, and checks some constraints on that bit. So it can, and in that case, the constraints are satisfiable, or this is a satisfiable instance. If you start with an unsatisfiable formula, the PCP converts it into a highly unsatisfiable CSP. Right? The verifier will not be satisfied with probability even 0.9. So sort of the probability satisfied is less than 0.9 or something like that. So, and it's NP hard to distinguish these two cases because it's NP hard to distinguish the SAT formula being satisfiable from unsatisfiable. So a PCP is kind of a way of converting or generating hard CSPs, which are kind of hard for algorithms, right? Unsatisfiable things, which algorithms cannot always tell they are unsatisfiable. So this is sort of a poor man's PCP in some sense, like I want to at least say how do these look when I try to construct them using HDXs, right? And what properties of them can make them hard for algorithms. Okay? So, and that's the kind of question we're going to study, or that's the kind of question. And so, as I said, again, this is a vehicle for introducing some properties that are nice. And yeah, I mean, this specific instance, whether you remember or not, doesn't matter so much. Okay. Everyone okay so far? Now I'm going to write functions, but they are F2 valued because I'll kind of work with these right-hand side. There are no plus minus ones anymore in the talk. I hope you can make that switch, and sort of hopefully that doesn't confuse you. So let's think of a face, which is a triangle. And let's think of an equation as x sub e, where e appears in this triangle. And think of that as some g sub s, where some g is some labeling. So so g is from x3 to f2. So this is one s for every, well, actually, let's just call it t, right? Triangles. Okay, and this is going to be my instance, and then we'll see what is G. Oh, what is S? No, it's T. Sorry, just T for triangle. Okay, so I'm going to choose. So I have to choose some complex. I have to choose some G, and then say that this can actually lead to a hard instance, and then I have to prove that algorithms cannot solve this instance. Okay, and as I said, we want to sort of study basically how do HDXs lead to kind of hard instances. This is a construction from kind of a paper with Irit, Dinur, Prahladh, sorry, in alphabetical order. And there is actually a much better construction using chain complexes in quantum codes, which is by Max and David Lin. And I'll say in what sense it's better, but these are just two references. Okay. So now our goal is to construct a kind of instance which has the following property. So let's call this our instance I. Yeah. Yes.
Here they are hard.
Yeah, I need to prove that, but yeah.
Yeah, you need to prove that.
Yeah.
Like the reason to exercise this change makes it.
Yeah, so I'll say it in a minute, but I mean, okay, I don't have a very sort of general argument, but yeah, I can say something about the properties. Okay, so and what we will show is kind of explicit instances such that they are kind of far from satisfiable. And by far from satisfiable, I mean that any actual assignment can satisfy at most some 1 minus beta fraction, okay, for some positive constant beta. But a fairly general class of algorithms given by, let's say, semi-definite programs, and if you don't know what they are, I mean, I won't use them, I'll say something simpler, but so semi-definite programs are powerful sort of so-called hierarchies of semi-definite programs, whatever they are. Think that these instances are completely satisfiable, so they cannot distinguish it from this unsatisfiable. This is what is the true case, right? So there is a gap in what any kind of algorithm based on semi-definite programming thinks the true value is, which is 1 according to it, versus what it truly is. I should say, by the way, like all of the things we did for CSPs and HDX with the other definition can be done using semi-definite programming hierarchies. It's a slightly more complicated algorithm, so I didn't quite get into it, but actually that can also lead to a somewhat better decoding radius for Amnon's code due to a result of Richardson and Roy. But yeah, I mean, sort of, I stuck with this regularity algorithm because it's simpler and also gives some ideas which are nice. Okay, going back. And the point here is these explicit instances. Otherwise, this problem was kind of well known or sort of understood. And for random instances, there is a result of Grigoriev from 2001 and an independent result of Schoenebeck actually from 2008, which show that if you just pick constraints at random and then pick the right-hand sides at random, with high probability, this is going to be an instance which semi-definite programs or some whatever class of algorithms cannot solve. And in fact, the gap is even optimal that actually no more than half is unsatisfiable, and SDPs think everything is satisfiable. So, okay, good. So that's, yeah. He does. Sorry? We now do. So, I mean, well, as of a month ago, right? So it's, yeah. So now we can probably make this, okay. There is a bit of a catch. So there are two parts to this. One is choosing the vertex expansion. The other is choosing the right-hand side. The right-hand side is actually trickier. So even if you look at a lossless vertex expander explicitly, you still have to choose the right-hand sides. And yeah, that I still don't know how to do. Sorry. Yeah. Yeah. Sorry? You only need one-sided expansion. Actually, yeah, sorry. So we don't need even these fancy new constructions. But the right-hand side is the issue. Okay, sorry. Okay, other questions? Okay, so forget about like semi-definite programs and so on. If I told you, here is a bunch of equations, can you prove they are unsatisfiable? Don't need to worry about how many fractions are satisfiable. Just prove to me that I can't satisfy all of them. How would you do it? Gaussian elimination. Okay, can you say a little more? Exactly. So, I mean, what would you do? You kind of take some linear equation, L1 equals B1, you kind of take some equation, L2 equals B2, and then you kind of combine them to derive L1 plus L2 equals B1 plus B2. And then maybe use this and maybe also this or something, and so on. Like, I mean, you can reuse your conclusions and so on. So you can think of this as like a DAG in which you keep deriving things. And at the end of the day, if you derive, let's say we always add two equations at a time, it's just easier. So the end of the day, the goal is to derive 0 equals 1. If you can do this, it's unsatisfiable. It turns out SDPs can't do much better. So there's actually, in these papers, there is basically a reduction that if you do this process and if you restrict yourself to sort of the any equation you derive in this process, in this proof, has to have at most W variables. And then, basically two-sided, but I'll say one side. If you cannot prove 0 equals 1 using less than equal to W variables in every equation, then neither can the STP in time. So, if W bounded Gaussian elimination fails, implies that n to the W over 2 time SDP fails. Okay, so now we'll just kind of focus on this task of just adding things. Okay? And the only catch is we are not allowed to have more than W variables in an equation. What is the largest value of W for which we can say that if I restrict you to W, you can't refute this? That gives me the best possible lower bound. Okay? So now our goal is just to add equations and see what happens. Okay? Everybody fine? Okay, so now let's see what it means to add equations. And so we have a complex. Let me draw it sort of slightly more geometrically. And each triangle corresponds to one equation. Every edge corresponds to a variable. Let's say you added the equations corresponded to this triangle, and I don't know, this triangle. Okay. Then, what are the variables that are there in the new equation that you got once you added these three equations? Exactly. So, the boundary. And this should remind you of something Pavel was talking about yesterday. So it's actually the same boundary operator. If things occur an even number of times, they cancel. If they occur an odd number of times, they stay. And what we looked at in random instances and so on is to say, if you add equations, how many things occur uniquely? So how many things are there which occur in exactly one equation? Okay? And those are, that gives you unique neighbor expansion, which Swastik was using, for example. And here we can do even weaker, I mean, like, or not weaker, but here uniquely is too much to hope for, but we can study how many things appear an odd number of times, which is just the boundary. Okay? And what we would like to say is that as we keep adding things, the boundary doesn't kind of cancel out, it doesn't vanish, right? So this is what we will call some kind of boundary expansion. So if you add a bunch of triangles, the boundary is somewhat large. And so to get the final conclusion, we'll say that, okay, you must have had to add a lot of triangles, and so the boundary must have been large at some point. Okay? And so you needed a lot of variables, and SDP would not have worked. Okay? That's roughly the plan. And so this is just the observation that adding gives you the boundary. Okay. Yeah. So let me first kind of write down what the boundary is. But okay, the plan is just to say, as you add more and more things, you get larger and larger boundaries. Then at some point you might get a fairly large, like if you after you've added a bunch of things, you will get a fairly large boundary. And that just means that the width is pretty large, this W, because the boundary is just a number of equations. Okay? And so you need an equation. So in any proof, if I can say that you have a large boundary somewhere, then you need a lot of variables in some equation somewhere, and so SDP could not have solved it just by that reduction. Okay, but I need to make this precise, and let me remind you of what this definition of boundary was. So formally we can define this operator, which, like Pavel denoted, I can denote this by a partial sign, and 3 just means I'm looking at triangles. Okay, and for any function f, which is, let's say, a function on triangles, so you can think of it as a subset of triangles if you like. I can define this function, which is a subset of edges. So it's the same as f2 to the x2 if you want. So it's a function on edges, okay? And it's defined as you think it is. So this function computed on the edge uv is just counting how many times this edge occurs. If you look at all triangles that contain this edge, and if these triangles are in your subset, you just add them. And if you have an odd number, this edge survives. If it's an even number, this sum is 0. This sum, all these things are over f2. So this is the same function that Pavel was writing in a slightly different way yesterday, but it's the same function. Okay. So that's the boundary function, and now our goal is to study how boundaries expand, or what I'll call some kind of boundary expansion. And I mean, basically my sort of hidden agenda is just to define boundary in some other kind of expansion. And this is a sort of nice application. Okay. There is one big problem with this plan, which is, suppose I have a complex, which is, and then at the end of the day, we'll look at some Ramanujan complexes or something which I'll not really need to consider what they are, but access some properties. But a complex, let's say, has triangles and also has higher order faces. Okay, so it has, let's say, triangles, tetrahedra, or kind of faces of size 4, and so on. Okay. Now, let's consider a tetrahedron. Okay. Or equivalently, combinatorially, let's consider a 4-face, and let's consider all 3 triangles in it. Sorry, all 4 triangles in it. And now, what is the boundary of these 4 triangles? So suppose I have a function f which is 1 exactly on those 4 triangles. Sorry? Every edge appears even number of times, right? In fact, exactly twice, I guess, right? So the boundary is 0. So there is a big problem with this plan, right? I mean, I got stuck at 4. So when I added the 4 equations corresponding to triangles in a tetrahedron, I got 0 on the left-hand side. If I'm going to be able to fool you, so my plan is to give you a bad G and your plan is to catch me. If I'm going to be able to fool you, it better be true that those 4 right-hand sides also add up to 0, so that you don't get 0 equals 1. 0 equals 0, I don't care. Right? Derive 0 equals 0, go home. So, okay. So it better be true. So, and this is nothing but the boundary of this tetrahedron. So it better be true that the function g that I'm trying to design for my instance is in the kernel of the boundary operator on 4 faces. So this is a constraint I need. If I don't have this, you can catch me very easily. Right? So I don't want you to catch me. Okay, good. So I need this condition. And now we will kind of try to study the same plan, but with this kind of condition that G is in this kernel. Okay, good. Now there is one other kind of piece of the puzzle, which is I want this instance to be unsatisfiable, because otherwise, I mean, you can't catch me, but I didn't do anything. So I want this instance to be unsatisfiable, and what does that mean? Let's check. Sorry? Yeah, but the delta, right? So yeah, I need to write that. So if you think about it, our functions were also, like our constraints were also obtained this way. So you think of variables on the edges. So now let's think of each variable as some function of this edge. Okay, and all I'm saying is that there is a G written on triangles such that when I sum of these functions, okay, so the boundary operator kind of said you go from a function on triangles to function on edges. Here I want to kind of look at a function on triangles that is obtained by summing things on edges. So it goes from triangles to, edges to triangles, the opposite direction. And this is called the co-boundary operator. So it's usually denoted by delta. And this is, this maps functions on, let's say, edges to functions on triangles. And now my constraint satisfaction problem can be written very succinctly. Okay, find an f such that technically as close, but I'm claiming you can't even catch if it's sort of satisfiable or not. Satisfiable means there is an f which is a labeling of the edges such that the co-boundary function or like the co-boundary operator applied to that gives me G exactly. That's what it means. Okay, but I don't want this to be satisfiable, so I want G to be in the kernel minus the image. Right? Right. So this should ring a bell. I mean, this is exactly what Pavel was doing yesterday. Oh, did I mess up? Sorry? Kernel of the 3rd level boundary operator. Okay. Let's see. Sorry, I'll just be a bit slow, but okay. Yeah, G is sorry. It's that right? Yeah, okay. It's in the co-boundary operator because I'm just saying when I okay. Yeah. So well, okay. Yeah, your job is to catch me, right? Not just in the proof. But this boundary operator takes me to a function on edges. I was actually talking about the co-boundary operator because so boundary operator is something we need expansion for. But I was talking about the co-boundary operator, which takes me from things to from triangles to tetrahedron, and things on each tetrahedron should be 0, right? If I add things, so it should be in the kernel of delta 3 and the image of delta 2. Okay, good. But that way I got to define both boundary and co-boundary operators. Okay, and the fact that for every tetrahedron it's 0 is nothing but the simple thing that like delta 3 times delta 2 is equal to 0, right? Or for any kind of I plus 1 and I is equal to 0. And similarly, for boundary operators, I minus 1 times I is equal to 0. Because they're actually transposes of each other. So, okay, good. So we defined boundary and co-boundary operators, and now our goal is to find this. Any question? It doesn't. It just implies that the thing is not satisfiable. And at least this simple check will not find a refutation, which is just adding things in the tetrahedron. Right. But yeah, we need much more. Yeah, so it doesn't yet. Okay. Okay, I have 10 minutes in which it should imply that, so let's do that. So, okay, so the fact that you don't have a short refutation, let's forget about this tetrahedron issue for a second. The fact that we chose G to be in the kernel of delta 3 will kind of take care of it. Okay, but let's not worry about it for a minute. Okay. Now, suppose I could prove that when you add any kind of I don't know, 200 equations, you get a boundary of size 20, whatever, something. It's not so it's some kind of isoparametric inequality, right? It's like saying you can't pack a lot of volume in a small area, in the surface area. Okay, so now let's look at this proof. How many equations did you need overall to derive this conclusion? It must have been more than 200, because otherwise you couldn't have got 0. You must have had 20 variables active. Okay, it could be much more. It could be 1,000,000. But at least one of the two equations you used to derive it must have had at least 100 equations that needed it, because otherwise I could have done that better. So at least one of them must have needed half of whatever this was. Let's talk about that equation. How many did you need to derive that? Either this is already kind of 200, in which case I already reached that, okay, this must have had a boundary, I couldn't have had derived it. Or either this one would have required at least like something like 200. Okay? So at I can keep going down in this complexity, and I'll at some point reach some intermediate equation which requires between 100 and 200 equations to derive. But then that one would have had a boundary. So if I prove that for a fixed size, I have a boundary, like for up to a fixed size, up to some size, then by this kind of intermediate argument, which is due to Ben-Sasson and Vigdusson, I can say that I reach an intermediate node where you must have had a boundary. And so you must have needed at least 20 variables. So SDPs of size n to the 10 could not have done this. Right? And so basically we need to prove that sets of triangles of at least some size have a boundary. Okay? Maybe not very, very large, but at least 200. Or, I mean, what we proved was something like log n. So that gave like n to the, and we proved that they have a boundary of size square root log n. So it got like n to the square root log n bounds for SDPs. And I mean, I'll not prove that. I just want to kind of define some notions which capture it, because you might need it in the workshop next week. But basically studying these notions, I just want to say that kind of the study of CSPs on HDXs that directly reduces to this kind of boundary and co-boundary kind of computations. There's some conditions corresponding to co-boundary, and there are some things coming from boundaries. Okay. And there's a third condition. If I really want is to be not just unsatisfiable, but really far from satisfiable, then I want this G to be very far from the image, right? It's sort of, or Rather, any G which is not in the image should have lots of ones. So I want this not just to be non-trivial, but a good code, let's say. If this is a good code, if this G has lots of ones, then all those equations where G is 1 will be unsatisfiable. So, or it will be far from anything in the image. So if I can say that anything which is here is actually far from the image, then I will get a really unsatisfiable system, right? Because the image is only satisfiable things. And so, yeah, so this is also the kind of thing Pavel was talking about. If you get this is a code, then you actually get strong unsatisfiability. You want kernel of delta 3 to be a code. Okay, good. So now let me just maybe make some definitions. And then, yeah, I mean, we won't prove things. I'll just kind of say that those definitions can be satisfied by some known complexes. Okay? And that's more or less enough for the proof. And let me define the boundary expansion, HI, as the minimum over F, and which is in F2 to the xi of the size of the boundary of F. So this will be del I divided by, so I don't want the size of F because, okay, or I should really look at the distance of F from something that I know is in the kernel. Sorry. I'm horrible at these deltas and partials, but unfortunately that's the standard notation. Okay, so, right, so this we already know is in the kernel. Right? So this I'm not going to count. It will trivially kind of, I mean, it will just give you infinity or something. So, but let's look at all the others. Also let's look at the F distance of F from this. So you can shift it so that you kind of look at the minimal guy, the smallest number of ones. You can add anything in the boundary. So, and now look at what is the size of the boundary of this F versus the size of F. Actually, I'm lying a little bit because if you have a complex, you have weights and so on. So you have to look at the sizes according to the distributions, like weighted sizes in each of these. But it's just weighted sums. I'm not going to write that. There is another problem on this definition, which will kind of become more obvious when we write the corresponding definition for co-boundary. So so this is the, okay, -1. This is the analogous definition for co-boundary expansion. Now, from the kind of G we were talking about, you already see that this has a problem. We were saying there exists a G which is in the kernel of delta 3 minus the image of delta 2. That kind of a G will just kill this. The numerator is 0, the denominator is not. Okay, so that sort of situation is called basically a non-trivial kernel for this delta 3, not just the image of delta 2, or equivalently the kind of quotient of these two is called the cohomology. So there is a non-trivial cohomology. And when there is a non-trivial cohomology, the kind of the better definition, which, I mean, sometimes the same notation is used. I'm just going to put tilde. I'm kind of going to fix this problem almost by definition. So I'm just going to say distance from the kernel. So this image is in the kernel, but there could be other stuff. I'm just going to take a distance from that. Okay, good. So now this definition makes sense. This is sometimes called co-boundary expansion. And this is called co-systolic expansion. And the fact that things in this kind of kernel minus the image are large is what is called co-systolic distance. Pavel was talking about systolic distance. So these are just names, but there's another nice interpretation of co-systolic expansion. It's just saying if I take the parity checks, then the number of parity checks that will be 1 is proportional to how far I am from the kernel. So this just says that the kernel of delta I is locally testable. Right? I can just check it by parity checks. So that is why this notion kind of also is very clearly related to local testability. And this kind of developed in a paper of Kaufman and Lobotsky, but I'll not talk much more about that. Okay, so as I said, we proved some fairly weak kind of boundary expansion that for things of size which is not even expansion in this definition, because here I need constant proportionality. We just proved for things of size log n, the boundary is at least square root log n, which is sufficient for our application, but not really enough. In general, proving co-boundary and co-systolic expansion is kind of hard for all functions. And there are some complexes for which we know how to do it, but it's even non-trivial for the complete complex. It's not something which is obvious. But we don't need it because we said we have this kind of intermediate sort of size argument that we can only prove it for equations of size up to like a number of equations which is at least 200 or almost 200 or something. So this is what was kind of studied in a paper of Max and David Lin, where they kind of defined what was called the small set boundary or co-boundary expansion. I mean, it's exactly as it sounds. You sort of restrict the size of f to some n over 1,000, and the rest of the quantity is the same. But let me just draw a picture which sort of sets up this correspondence a little. So the cool observation was that we kind of looked at basically three things: triangles, edges, and tetrahedron. And then we had these kind of boundary operators and these co-boundary operators. I'm sorry? Oh, that's delta 3. Thank you. Okay. And now this was used to kind of define the CSP. We said delta 2 of f is equal to g. This is what we need boundary expansion for. To say that when you add a lot of triangles, you get a lot of edges. And this was used to kind of do some local checks that if you add things in a tetrahedron, things should be 0. So we had to be careful about this. So we had to look at something which was in the kernel of this and not in the image of this. These are three things we needed. And the cool observation, well, much more than an observation, but the cool thing in their paper is to say, well, let's look at chain complexes. So Powell defined chain complexes this way, that you have some f2 to the mx, you have f2 to the n. And let me write the arrows this way first. And then you have hx transpose, you have hz, you have hz transpose, and you have hx. These are also local operators. Every kind of entry depends, like these are sparse matrices. So every entry after applying this matrix depends on constant number of entries in the starting vector. Right? So you can basically plug in this picture instead of this one. And then you can work with any kind of chain complex. You don't have to work at these kind of boundary co-boundary operators on a simplicial complex or on some usual high dimensional expander. Okay? And there we get all these properties from the corresponding things about quantum codes that Pavel talked about a little bit and will probably tell you more. But the fact that the kernel minus image has a large distance is basically the same thing as saying if you look at these codes, then if you look at, let's say, Cx minus Cz perp, then this has large distance. And we want them to be codes, so they better have large distance. The boundary and co-boundary expansion also comes, and it turns out that these codes also give you, like the same construction also gives you locally testable codes. So the only thing is, just like the argument that Swastik gave for Sipser-Spielmann, you don't get like unique neighbor expansion for everything. You just get it for small enough sets. Okay? So you get this small set boundary or co-boundary expansion. How small? Sets of size n over some large constant. That's pretty great, because if you have boundary or co-boundary for subsets of size n over something, then you say that you need omega of n variables in intermediate equations, which gives you exponential bounds for SDPs. Okay? So that's what you get using this. But yeah, I wanted to use this as a vehicle for introducing some of these concepts, and I guess you'll see more of them in the workshop. Should we? Yeah, let's stop here. Questions? Yeah. Actually, the distance is true for Cx minus CZ perp, and not just in the coset sense. So this is something Pavel said yesterday, that it's equivalent to saying that any vector here has large Hamming distance in the usual Hamming sense, not this coset Hamming thing. So it's equivalent. But yeah, here I just mean this. And so for our construction also, we pick an arbitrary G, which is the kernel minus image. Minus. Don't have to do cosets. Yeah.
Usually in the previous construction, there is one possible issue that if 3 triangles, 4 triangles come to 0.
Yeah.
You still use the right hand set cleverly so that
Yeah. Good.
This does not happen here. Right?
It can happen here. It can. Yeah, it can also happen here, I think. Yeah. So the thing is, just right. No, this was just coming from the fact that, oh, I guess there is no higher level maybe, but no. I still have this, right? It's No. So this is an issue for CZ perp. So so why did I what did that mean here? That if I looked at delta 3 times delta 2, something which was in the image of delta 2, then delta 3 times delta 2 is 0. Right? And these equations were just in the image of delta 2, just adding all these things, right? So here it can still happen that if I look at some element of Cx which corresponds to CZ perp, adding that will give me 0. Okay? So there I have to be, this G has to be outside of CZ perp. That is the issue here. The triangles correspond to a CZ perp code word. And CZ perp has small weight code words. Yeah, so in the denominator, we always divide by distance of f from the image, right? So it's not just the size of f, it's the distance of f from the image. But if f is in the image, then all bets are off. Right? So that's the issue here that happens.
So the right hand side
yeah, it still matters. So you have to, but it matters only the same way it does here, that here we had to choose something which was in the kernel of delta 3 minus image of delta 2. Here we look at something which is in Cx minus CZ perp. Okay, but the CZ perp is what the image of delta 2 is. Other questions? All right, let's get lunch.